Hi dears. So this is your operational amplifier circuit, and I understand it must be a Smith trigger circuit, positive feedback, a modified comparator design which is most advisable for wave shapings and multi-vibrators. So dear students, here we need to calculate upper threshold point as well as lower threshold point. Students, it is well known to find upper threshold point, to find plus V reference or upper threshold point, no doubt V naught must be taken it as a plus VCC. Am I right here? So let me take this as a plus 14 volt plus VCC. So if it is plus VCC, I understand diode act as a short. Implies diode act as a short or a forward bias if we choose it as an ideal diode for simplification. Once it acts as a short, these two resistors act as parallel. Therefore, now this voltage, which is a feedback voltage, that feedback voltage acts as upper threshold point as well as lower threshold point. Therefore, the feedback voltage now, which is none other than upper threshold point, will be, as input current is neglected, note that the same current will pass between the two resistors after parallel connectivity of 72k ohm. So you will be getting it as V naught into 12k whole divided by 12k plus 72k parallel 72k. Am I right here? Right. So V naught into 12k whole divided by 72, 12k plus parallel resistance of 72k, or otherwise I could simply write it as a 36k. Right. So therefore, if I substitute the value as 14 volt plus 14 volt instead of V naught and simplify, I will be getting it as a 3.5 volt. That's upper threshold point value. Similarly, to find lower threshold point, no doubt V naught act as minus VE. Minus VE is given as minus 14 volt, right? So once it is minus 14 volt, I understand diode act as open switch. Once diode is open, this branch can be taken as open. Hence, I should take only, or I should include only 72k in this parallel connectivity. Therefore, the feedback voltage, which is lower threshold point, none other than V naught into 12k whole divided by 12k plus 72k, where here this V naught value is nothing but minus 14 volt. Am I right? So if I substitute that and get simplified, I understand you will be getting it as a minus 2 volt. Hence upper threshold point is 3.5 volt and lower threshold point is minus 2 volt for the given Smith trigger circuit. Thank you so much. So it was clearly mentioned this is a transconductance amplifier. Now we need to find the input resistance for the design. So dear students, the universal formulae for input resistance is always input voltage by input current. So let me understand this must be the input current, right? The same parallel connectivity, I can take it this is the input voltage itself. So dear students, if I apply KCL over there, input current is equals to V in by 3k. So this current plus this current. I understand this current can be this current because load is open circuit. So plus 0.33 into 10 power minus 3 into V in. Right? Therefore, if I take V in as common, so I in equals to V in as common 1 by 3 into 10 power minus 3 plus 0.33 into 10 power minus 3. Therefore, now it is very easy for us to find input resistance by IN if it has 1.5 kilo ohm, which must be the final answer to find input resistance. Thank you so much.
In the given circuit, examiner is asking us to identify the region of operation of BJT. To decide the region of operation of a BJT, we should know what kind of biasing is given to emitter junction of BJT and what kind of biasing is given to collector junction of BJT. Now, let us look into the circuit here. If you look into the circuit carefully, base and emitter are shorted, means the effective voltage at base and effective voltage at emitter is 0. Therefore, the base current into the circuit is 0. Therefore, emitter junction is reverse biased. On the other hand, if you observe the voltage between collector and base, which is VCB, and is found to be minus 10 volts. That means, in an NPN transistor, as collector is N-type semiconductor and base is P-type semiconductor, between N-type collector and P-type base, it is found to be a negative voltage existing. As a result, collector base junction is forward biased. Therefore, with emitter junction reverse biased, collector junction forward biased, the device is said to be operated in inverse active region or reverse active region. In a common emitter amplifier, which of the following statement is true? That is what the question given to us. Out of the 4 statements given, option C is correct option. That is, in a CE amplifier in mid-band region, coupling capacitors are short-circuited and junction capacitors are open-circuited. Let's see how. Considering, in case 1, let us consider coupling capacitors. Of course, coupling capacitors are the capacitors that are connected externally in the amplifier circuit. Generally, their range is of the order of microfarads. Therefore, at mid frequencies, considering the reactive impedance of coupling capacitors as 1 by 2 pi Fc, means F is, in the mid frequency range, F is of the order of few kilohertz and capacitance value is of the order of microfarads. Therefore, 1 by 2 pi Fc together will be very high. Therefore, the coupling capacitance reactive impedance at mid-frequency range may be more or less equal to 0. Hence, they simply act like short circuits. On the other hand, coming to junction capacitors, generally, junction capacitors are the internal capacitors of the device, and the range of these device internal capacitors generally of the order of picofarads. As a result, at mid frequencies, if you consider the reactive impedance of junction capacitors again as 1 by 2 pi F at mid frequencies generally of the order of few kilohertz to few hundreds of kilohertz, and junction capacitance value is of the order of 10 power minus 12 picofarads. Altogether, the total denominator value is of the order of 10 power minus 9, and so as a result, the total reactive impedance of junction capacitance, effective reactive impedance of junction capacitance at mid frequencies is more or less infinite or very high. As a result, we can conclude that junction capacitors will act like open circuits at mid frequencies. So, option C is correct. In this question, we are supposed to answer for improving the performance of differential amplifier using BJT. what are the conditions required or what are the facilities we should provide? That's what the question is actually. Where out of the 4 statements given, we can say the value of CMRR is increased by increasing RE, and increasing beta and RC increases differential mode gain. Means statement 2 and 4 can be considered as correct. Means option D is correct. Let us see how. We know in a differential amplifier, CMRR equal to differential mode gain by common mode gain. For high value of CMRR, from that equation number 1, what we can say is, for high value of CMRR, the common mode gain should be as low as possible. But common mode gain in a dual input balanced output differential amplifier is given by RC by 2RE. That means by increasing RE, we can reduce the value of common mode gain. That means what? If you reduce the value of common mode gain, you can increase the value of CMRR. Therefore, what we can conclude is, by increasing the value of RE, we can increase the value of CMRR. That means statement 2 is correct. On the other hand, the differential mode gain in a dual input balanced output differential amplifier is given by GMRC. But GM is nothing but HFE by HAE. But HFE is nothing but beta. Therefore, differential mode gain equal to beta RC by HAE. Therefore, by increasing beta and RC, we can increase differential mode gain. Means statement 4 is also correct. Altogether, statement 2 and 4 both are correct. Means option D is correct. In this question, examiner is asking us to calculate slew rate. Basically, slew rate of an op-amp can be defined as the maximum rate of change in the output voltage of an op-amp is nothing but slew rate of the operational amplifier. That means, slew rate is equal to, mathematically slew rate can be given by slew rate equal to dV naught by dt maximum. Look at the waveform given. It's a triangular wave given to us. Right from t equal to 0 up to 5 microseconds, means half of the total time period of 10 microseconds, the signal, output signal is rising towards maximum of 10 volts. That means the output is increasing from 0 to 10 volts by a period of 5 microseconds. As a result, we can simply write dV naught as 10 volts and dt as 5 microseconds. Therefore, slew rate in the present case is equal to 10 volts by 5 microseconds. So option C is correct. In this question, examiner is asking us to match the 2 columns of parameters given for us. Where we know in a voltage amplifier, input is voltage. That means series mixing at input. In the same voltage amplifier, output is also voltage. That means shunt sampling is to be done at the output section. As a result, in voltage amplifier, series mixing at input and shunt sampling at output. Considering current amplifier as reference here, we know in a current amplifier both input and output are currents only. As a result, since input is current, shunt mixing at input is required. Since output is current, series sampling at output is required. Coming to transconductance amplifier, in transconductance amplifier input is voltage, therefore series mixing is to be implemented at input side. Since output is current in transconductance amplifier, series sampling is implemented at output side. Then finally, in a trans resistance amplifier, input is current, hence shunt mixing is required at input side, and output is voltage, therefore shunt sampling is required at output side. As a result, by considering all these discussions I have made into account, we can conclude that option D is correct. Okay, ma. In this circuit, examiner has given the Zener breakdown voltage as 6 volts, Zener knee current or IZ minimum value of 10 milliamps given, and examiner is asking us to calculate minimum value required for this RL, minimum value of RL permitted for satisfactory voltage regulation in the given circuit. For the estimation of RL minimum, first of all, what we do is, because RL is linked with V0 and IL values, let us first estimate output voltage. Look at the circuit carefully. Output voltage is nothing but Zener diode breakdown voltage, means V0 equal to Vz equal to 6 volts. Then, by applying KVL for input loop here, we can simply estimate source current supplied by the source, Is is given by 10 volts minus output voltage, means 6 volts by Rs, 40 ohms, which will give us Is equal to 100 milliamps. Then, for the estimation of IL, what we do is, let us apply KCL at node A and write an equation. That equation is Is equal to IL plus Iz. But actually what we require is IL, that too IL maximum. For the estimation of RL minimum, IL maximum is required. So, let us rewrite this equation number 3 as IL maximum equal to Is minus Iz minimum. Is is estimated as 100 milliamps, Iz minimum is given as 10 milliamps, therefore IL maximum becomes 90 milliamps. Then look at the circuit. From the circuit, RL is nothing but V0 by IL. That is what I wrote in equation number 5. But when we want RL minimum, the same equation can be modified to V0 by IL maximum. That is 6 volts by 90 milliamps, which gives us 66.67 ohms. In this question, examiner is asking us to identify the function of diode in the given circuit. To know the function of diode in the given circuit, what we do is, first let us consider the circuit without diode. Without the diode in case 1, it is a basic astable multivibrator. In a basic astable multivibrator, the formula for duration of positive half cycle is, of course, the charging period of the capacitor will decide the duration of positive half cycle, and during the charging period of the capacitor is going to charge from the power supply via RA, RB and C. Therefore, the on time or duration of positive half cycle is given by 0.69 into RA plus RB into C. Since RA, RB, remember, without diode we are estimating this. So, RA is 20K, RB is 20K. As a result, T on becomes 1.38 milliseconds. In the same circuit, when the capacitor is discharging via RB only, capacitor is going to discharge, because pin number 7 is connected to the discharge transistor internally there in the timer. Therefore, capacitor is allowed to discharge via RB only. Therefore, the discharging period of capacitor, nothing but duration of negative half cycle of output of 555 timer in a stable mode, is given by 0.69 into RB into C, which will give us 0.69 milliseconds. Now, consider case 2, wherein this time let us assume the diode is placed in the circuit. As a result, during the charging period of the capacitor, what happens is, since the output is positive, when it is supplying positive current via this branch into this RB capacitor branch here, the diode gets on, will automatically make this RB shorted. As a result, during the charging period of capacitor is going to charge via RA only. Therefore, the formula for T on, or the duration of positive half cycle, is given by 0.69 into RA into C, which will give us 0.69 milliseconds. During the negative half cycle, or during the discharging period of capacitor anyways, because when capacitor is discharging via RB towards 0, this diode becomes open and the resultant circuit will be normal stable multivibrator. As a result, the discharging period of capacitor will be simply equal to, or T of the duration of negative half cycle of timer is simply equal to 0.69 into RB into C. As a result, its value is 0.69 milliseconds. Now, if you compare the case 1 and case 2, where the duration of positive half cycle of the output without diode is 1.38 milliseconds, and the duration of positive half cycle in the same circuit with diode is 0.69 milliseconds. That means the diode in the circuit will reduce the duration of positive half cycle. That means option D is correct. In this question, examiner is asking us See, let us consider the 4 practical amplifiers that are required by a consumer, which are voltage amplifier, current amplifier, trans conductance amplifier, and trans resistance amplifier. Of course, in a voltage amplifier, the input signal is voltage. Therefore, series mixing is required. Once if series mixing is implemented, input resistance of the amplifier increases. Ideally, Ri value will be infinite. In the same voltage amplifier, output is voltage. In case if output is voltage in an amplifier circuit, shunt sampling is to be implemented. Shunt sampling leads to decrease in output resistance. That means ideally R0 will be 0. Then consider current amplifier. In a current amplifier, input signal is current. Therefore, shunt mixing is to be implemented. So shunt mixing will decrease the input resistance. Ideally, Ri will be 0 in this case. In the same current amplifier, output is current. If output is current, series sampling is to be implemented. Series sampling always increase the output resistance. So ideally, R0 can be considered as infinite. Then considering trans conductance amplifier, input signal is voltage. So series mixing is required. Series mixing will make input resistance infinite there. And in the same amplifier, when output is current, series sampling is implemented. Therefore, output resistance becomes infinite. Finally, in a trans resistance amplifier, input is current. Therefore, shunt mixing is required. Shunt mixing will automatically reduce the input resistance ideally to 0. And output in the same amplifier is voltage. If output is voltage, shunt sampling is required. Shunt sampling will automatically reduce the output resistance to ideally 0. So, option D is correct. In an amplifier circuit, operating point is a function of IC value and VCE value in the amplifier circuit. But VCE is also depends on IC value. However, IC depends on three very important parameters which are actually considered as device parameters, namely IC0, the reverse saturation current of BJT, VBE, the junction voltage of BJT, and beta, the current gain, short circuit current gain of BJT. The reference equation, current equation of BJT, IC equal to beta IB plus 1 plus beta times of IC0 is the evidence for these issues I have mentioned here. Then, coming to the statement 1 given by the examiner, in case of BJT, the bias point drift from the design point of operation. Yes, always operating point will be drifted from the located position because operating point is a function of IC, but IC depends on IC0, VBE and beta. Therefore, if beta or VBE or IC0, which are the device parameters of a BJT, varies because of temperature, automatically IC gets varied. If IC gets varied, automatically VCE gets varied. With IC, VCE varies, automatically operating point or bias point will be drifted. So, statement 1 and 2 both are correct, and statement 2 is the correct explanation of statement 1. So, option A is correct. In this question, in statement 1, examiner has given in a differential amplifier, high value of emitter resistor provides high CMRR. Let us consider the explanation for that. In an op-amp, CMRR is given by AD by AC, means differential mode gain to common mode gain. Of course, CMRR is, even though discussed in terms of op-amp, but is generally estimated with respect to differential amplifiers. So, AD in a dual input balanced output differential amplifier, AD is actually GM into RC. In the same dual input balanced output differential amplifier, differential common mode gain AC is given by RC by 2RE. Means CMRR becomes 2 GM into RE. That means a high value of emitter resistor, if you increase RE value, automatically CMRR will increase. That is, high value of emitter resistor will automatically provides high CMRR. Therefore, statement 1 is correct. Then, let us consider the second statement. A differential amplifier with high CMRR will have less tendency to enter into common mode. Yes, this is also correct. Let's see how. In an operational amplifier, the percentage error in the output of op-amp due to common mode, the error in the output of op-amp due to common mode is given by 1 by CMRR into common mode or input voltage by differential mode input voltage. Then, when you want error in the output of op-amp due to common mode to be very low or ideally 0, the value of the CMRR must be infinite ideally or as high as possible. That means an op-amp with high CMRR will have the less tendency to enter into common mode of operation, or an op-amp with infinite amount of CMRR in ideal case will never enter into common mode of operation. Therefore, error in the output due to common mode will be 0. Therefore, statement 2 is also correct. However, statement 1 and statement 2 are individually correct, but statement 2 is not the correct explanation of statement 1. So, option B is right.